Okay, the problem that we were working on for this day seemed kind of funny. We were talking about flowers and things like that. But here's the basic idea. On the previous day, we showed that we could write a mass on a spring with spring constant k as d squared x dt squared was minus k over m times x. My point today is that no matter what shows up, if you have a second derivative with respect to time equaling minus something proportional to the actual function itself, the displacement, then what you have is simple harmonic oscillation. So the idea is that even if we have k over m or something else, we can represent that as anything, which I like to draw as a little flower here, but we can represent it as anything. So the idea here is that if you were to play around with functions looking for a solution here, you might eventually, and you probably would, try something like this. So you would try something like a cosine of omega t plus phi. In fact, maybe you would just try something as simple as y is cosine omega t. But that's fine too. That's simply a more specific case of the solution. So if this is our guess, what we do then to check is we actually do what it says. It says on the left-hand side to take two derivatives. So the first derivative, dt of the first derivative, which would be minus omega sine of omega t. And then we would say that that's equal to, on the right-hand side, minus flower times y. So we'll take the next derivative, just like it says. So that's minus omega and another omega cosine omega t equals minus flower. And now we'll just write down what it says y is. So we'll write y over here, and this is just cosine omega t. Now, if we'd gotten that some sine function equals some tangent function or something like that, that really can't be true for any time you pick t. But this can be true because, in fact, as long as 2 omegas is equal to flower, forgot the stem on this one, then this is a solution. So if omega squared is flower, then cosine works. Okay, so the next question is then, what's the period? Well, what we think to ourselves, is that cosine omega t repeats when omega times t has become 2 pi, starting from 0. And in this case, then, we kind of have this aha moment that the t in this case is the period. That's what we mean for the time to repeat. So we get that the period is just 2 pi all over omega. Okay, 2 pi over omega, and then from the previous page, we have that omega is equal to the square root of flower. So the frequency, so let's start with the period. So the period is 2 pi all over the square root of flower. And we know that frequency, measured in cycles per second, as opposed to the period, which is seconds per cycle, frequency is 1 over the period, which is just 1 over 2 pi times the square root of flower. So you should check from what we did last time, you should check that we showed that the frequency of a mass on spring was, let's see, 1 over 2 pi square root of k over m. And in fact, that is what we got. Okay, good.